Hello everyone, and this is Dr. Lennon, and we are going to kick off another lecture on improper integral examples. So these are integrals where we're looking at limits that go to infinity and determining whether they diverge or converge. And if they converge quickly enough, often they can approach a finite sum. So typically the techniques involved are the same, techniques of integration, but fall back on some of the limits that we looked at earlier. So a lot of times they'll just be shortcuts. Sometimes they'll be u substitutions. I didn't see any integration by parts examples in the exercises, but we'll go through a couple, and then I'll give you a couple to look at, and then we'll go over them on Friday in class before you head off to spring break next week. So let's get started. So this first example is the integral from 3 to infinity of 1 divided by the quantity x minus 2 to the 3 over 2 power. So as we discussed on Monday, that exponent right there, which we were calling the p-series test, if the exponent when it's in the denominator is bigger than or equal to 1, actually if it's bigger than 1 we get convergence. If it's less than or equal to 1, we're going to get divergence. So we already know that this integral is going to converge. And basically what you do is you just integrate it as normal and replace that infinity with a limit as t goes to infinity, and then just try and plug in as normal. So how would we integrate 1 over x minus 2 to the 3 over 2? Well, we'd think of that as x minus 2 raised to the negative 3 over 2 as a power. And again, you don't have to worry too much about any type of chain rule here, because the derivative of the inside x minus 2 is just 1. So what we do is we just add 1 to the power and then divide by that number. So if you add 1 to negative 3 over 2, you get negative 1/2. And 1 divided by negative 1/2 is negative 2 over 1. It's just the reciprocal of that fraction. So we're looking at the limit as t goes to infinity of this negative 2 over 1 times the quantity x minus 2 to the negative 1/2 from t to 3. So basically we're going to evaluate, plug in t for x, and then subtract and plug in 3 for x. So we get negative 2 over 1 times the quantity t minus 2 to the negative 1/2, and then minus negative 2 over 1 times 3 minus 2 to the negative 1/2. So that second part is actually going to simplify quite a bit. The two negatives come out to positive 1, and 3 minus 2 is 1. Negative 1/2 is just 1 divided by the square root of 1. So the other part, though, if you look at the limit, basically, as t gets very big, the square root of t is going to get very big. So basically, that negative 2 divided by the square root of t minus 2 quantity, that first quantity that the limit actually applies to, just goes to 0. So 2 over a very large number approaches 0. So we say the limit as t goes to infinity of that is 0, so we end up with just 0 plus 2, and that equals 2. So you may want to fill in a few details there if you're confused, and ask me some questions on Friday. But that is essentially how we get that limit. So our initial reaction that it's going to converge to the p-series test is confirmed. Okay, so let's look at a second example. So we're looking at the integral from negative infinity to negative 1 of e to the negative 2x. Now, we can do this the same way formulaically, but we can also confirm it graphically. So my intuition going from negative infinity to negative 1 is that this is somehow going to diverge. And if you think about that, let me just, let's draw the graph on, say, Desmos. So if we look at the graph here, say y equals e raised to the negative 2x power, then what's going on? Well, we get this graph, and so going from negative infinity up to negative 1 is basically all the area below this whole thing. So, I mean, we might even be able to say, okay, what's the integral here from negative, I don't know if they have any infinity symbol. Oh, they sure do. Negative infinity to negative 1. Probably it doesn't. It's confused because it's divergent, basically. Maybe I got to put a dx. Okay, it says undefined, but really what's going on, if you look at the picture, we're getting some quantity that's very large. So we'll look at that in a second. But basically it's the area below this, and as you go over, it's just bigger and bigger. So if we go back, we can do the same thing. So the antiderivative of e to the negative 2x over negative 2. So let me get this back in the view mode. That'll probably help. But basically, how do you do the antiderivative of e to the negative 2x? Well, it's e to the negative 2x over negative 2. It's that exponential rule for e to the kx. Then plug in both t. So we're going to change the negative infinity to t. So we're taking the limit as t goes to negative infinity. Change x to t. And then the other one, negative 2 times negative 1 is going to be positive 2. So we're going to get, some plus e squared over 2. But the thing is, the e to the negative 2 over negative 2, that's going to go to positive infinity, as we saw, because that area below the graph is so big. So if you look at, say, e to the negative x, in general, as you go to the left, that's going to be an infinite quantity. And if you would look at e to the positive x as you go to the right, that's going to be infinity. So basically, this limit is, this integral is going to diverge. It does not have a finite area. So that's basically what I'm saying there. If you look at the limit of e to the negative 2t as t goes to negative infinity, you get something that goes to positive infinity, so it's divergent. So the whole integral, actually, because we're taking that quantity and dividing by negative 2, it's probably actually going to go to negative infinity, but for our purposes, we just care whether or not it converges or diverges, so we can just say this diverges. Okay, so let's go to one last example that involves a u substitution. So we're taking the integral from e to infinity of 1 over x times natural log of x cubed. So this is going to be a u substitution as we've seen before. And as with previous problems, we are going to be able to change the limits. Yes, even if one of those limits is infinite, giving us an improper integral, we can still change the limits, but now we have to use a limit. So that's what this first note is. So basically, our choice of u is going to be the natural log of x, because then du will be 1 over x times dx. So the integral will just become 1 over u cubed times du. So now we have to think about what are the limits going to do. Well, if we think about when x equals e, how do we get u? Well, we just take the natural log. So the natural log of e is equal to 1. So when we move to our u substitution integral, the bottom limit will change to 1. And as x goes to infinity, the natural log of x also goes to infinity. Therefore, as x goes to infinity, u goes to infinity. So our integral limits will change from e to infinity to 1 to infinity. So basically, that's what our new integral looks like. And if we're going to evaluate that, we think of it as u to the negative 3rd power. We add 1 to the power, then divide by that number. So we get u to the negative 2 over negative 2. Plug in t. And basically, t to the negative 2, that's again something like 1 over t squared. And as you plug in infinity, or think about that quantity growing larger and larger, you've basically got a fraction where the denominator is getting bigger and bigger. So that quantity gets nearer and nearer to 0. And then when you do minus 1 over negative 2, that's 2 negatives, so that becomes plus 1 over 2. So basically, the limit converges to 0 plus 1 over 2. So we have another example of a convergent integral. And this integral converges to 1/2. So these are, the first two examples are pretty basic. We saw a convergent integral, improper integral, and a divergent improper integral. Again, if we ever have a polynomial raised to a power in the denominator, we have the p-series test, so we know immediately whether it converges or diverges. But sometimes the integrals are a little bit more complicated, and we may have to use some other techniques like u substitution. So the two that I would like you to try for Friday. So I'm using a slightly older file, so let me pause and get that fixed. Okay, sorry for that break. I was just on an older version of the file, so now I've got the correct one. So the two I'd like you to try for homework are pretty similar to two of the ones that we've done. So the first one is just a straightforward integral where you've got e to the negative 3x from 0 to infinity, and I will tell you that this should converge. And then when you look at the second one, we've got a polynomial, but notice this is a u substitution. So you're going to want to let u equal x squared plus 2, and then try to integrate from there. So if you have any questions on any of these, then let me know. Again, you can read the textbook. So this is section 6.5 in the calculus text that we're using. But I think these are pretty fair. Friday we may look at a word problem or two, and perhaps I'll give you a take-home quiz for spring break. So just let me know. And if you would like to meet Friday morning, I shouldn't have any problems coming in a bit early. All right, so this is Dr. Lennon signing off, and I will see everyone on Friday.